All right, let's dive right into this explainer by asking a really simple but profound question. How exactly do the invisible forces of heat shape the physical world around us every single day? I mean, we experience heat constantly, right? But the actual nuts and bolts mechanics of what it's doing to matter on a microscopic level, that's entirely hidden from the naked eye. Well, today we're going to unlock those secrets.
To answer these everyday mysteries, we first have to wrap our heads around the fundamental thermal properties of matter that basically dictate how our entire universe behaves. Think about it for a second. Why on earth does a blacksmith go through the trouble of thrusting an iron ring into a roaring fire just to fit it onto a wooden wheel? Or, hey, why is it that when winter rolls in, a lake freezes at the surface, creating that thick sheet of ice, while the water underneath miraculously stays liquid?
So, here's our roadmap for today. We're looking at heat versus temperature, measuring the invisible, why things expand, the capacity for heat, and changing states of matter. By the end of this explainer, those everyday mysteries are going to make perfect sense. Section 1. Heat versus temperature, and why they are absolutely not the same thing. We throw these words around interchangeably all the time, but in physics, making a strict distinction between them is our vital first step.
See, heat is the actual energy on the move. It's the literal energy being transferred between two systems just because there's a difference in their temperatures, and we measure that energy in joules. Temperature, on the flip side, is just a relative measure. It's simply an indication of how hot or cold an object is compared to its surroundings, measured in Kelvin or Celsius. So to put it simply, heat is the actual energy traveling from your hot cup of tea out into the cold room. And temperature? Well, that's just the thermometer reading of the tea itself.
Moving on to Section 2. Measuring the invisible, including thermometers and absolute zero. So, now that we actually know what temperature is, how do we accurately measure it when our own sense of touch is, let's be honest, pretty unreliable? Scientists figured out a long time ago that human perception is just way too limited for science. But they noticed something amazing. Low-density gases obey really specific mathematical laws, completely regardless of which gas you're actually using. Enter the highly elegant ideal gas equation, PV equals mu RT. Because pressure and volume are directly proportional to temperature, scientists realized they could just hold the volume of a gas constant and measure the temperature simply by looking at the pressure. It is such a brilliant workaround for measuring something completely invisible.
But what's really fascinating is what happened when they actually tested this out. They plotted the pressure of various gases against their temperatures. Now, because gases turn into liquids before getting too ridiculously cold, they had to mathematically track the data backward. And by extrapolating that data all the way down to where pressure would theoretically hit zero, they made a massive discovery. All those different lines converged at the exact same point. They found the absolute minimum temperature possible for an ideal gas.
That ultimate floor of temperature is exactly negative 273.15 degrees Celsius. We call this absolute zero. It is literally the absolute foundation of the Kelvin scale, where negative 273.15 degrees Celsius simply becomes 0 Kelvin. It's the bottom of the barrel. There is, mathematically speaking, absolutely nothing colder in the universe.
All right, Section 3. Why things expand. The expanding world. Let's take a look at how adding heat physically changes the dimensions of matter. Spoiler alert, this is where we actually solve our first mystery. Normally, when you add heat to a substance, it expands in length, area, and volume. And hey, this totally explains our blacksmith. They heat that iron ring up so it expands, easily slip it over the wooden wheel, and then as it cools down, it contracts super tightly right into place. But water has this incredible, highly anomalous behavior. Unlike almost everything else out there, water actually contracts when it's heated from 0 to 4 degrees Celsius, its volume actually decreasing, making it denser. Crazy, right? And this quirky little anomaly is exactly why aquatic life actually survives the winter. As a lake cools down, the water hits 4 degrees, becomes incredibly dense, and just sinks straight to the bottom. So that colder, less dense water stays floating up at the surface and freezes there, which creates this perfect insulating layer of ice while the fish swim around happily in the liquid water down below. Meanwhile, other liquids react quite normally to heat. Alcohol, for example, expands significantly more than mercury or Pyrex glass for the exact same rise in temperature. Moving to Section 4, the capacity for heat, absorbing the energy. Have you ever wondered why the sand at the beach literally burns your bare feet on a hot summer day, but if you run under the ocean water right next to it, it's freezing cold? I mean, they're sitting right there, under the exact same sun. Well, the answer lies in something called specific heat capacity. Water has an exceptionally high capacity for heat, clocking in at 4,186 joules per kilogram Kelvin. Compare that to sand and glass at just 840, or iron at a measly 450. Basically, this means it takes massive amounts of heat energy to warm water up compared to dry land. Because water warms up so incredibly slowly, the ocean stays nice and cool on a hot day, and that temperature difference is exactly what drives those refreshing winds we feel at the beach.
And we can actually measure this specific heat capacity right in a lab using a process called calorimetry. It's pretty straightforward. You drop a hot object, let's say an aluminum sphere, into a known mass of cold water inside an isolated container, which we call a calorimeter. Then you just wait for the temperature to stabilize, which is what we call reaching thermal equilibrium. Finally, because no heat escaped that isolated system, you calculate the specific heat using one core foolproof rule. The heat lost by the hot aluminum must exactly equal the heat gained by the cold water.
Okay, final section, number 5, changing states of matter, specifically melting, boiling, and sublimating. Now that we know how things expand and absorb heat, what happens when they absorb so much energy that they literally can't get any hotter and they have to change entirely?
The absolute most crucial thing to understand here is that the temperature of a substance actually stops rising while it melts or boils. Seriously, if you heat a pot of boiling water, it won't get a single degree hotter than 100 degrees Celsius until every last drop is vaporized. The added heat is entirely used up, breaking the molecular bonds and changing its state. This exact mechanism is also what causes amazing phenomena like sublimation, where dry ice turns straight from a solid into a gas, or regelation. That's when pressure temporarily melts ice, creating a super thin layer of water that allows ice skaters to glide so effortlessly.
This incredible energy that's responsible for the transformation is known as latent heat, and the word literally means hidden. It's this hidden amount of heat transferred during a change of state without any change in temperature. It acts like this secret engine working behind the scenes of every melting ice cube and boiling pot of water in your kitchen. And incredibly, if you map out the pressure and temperature curves for these states of matter, you hit this almost magical spot called the triple point. For water, this happens at precisely 273.16 Kelvin, at a very specific low pressure. At this exact, precise number, ice, liquid water, and water vapor can all coexist in perfect thermal equilibrium at the exact same time. It is just this delicate, truly beautiful balancing act of physics.
It's pretty wild to realize that just a tiny quirk in thermal expansion, water becoming less dense right before it freezes, literally saves all aquatic life and makes our planet habitable. Without that massive specific heat capacity, our climate would be completely unrecognizable. It kind of leaves us to wonder, doesn't it? As you go about your day, feeling the sun on your skin or just putting the kettle on to boil. What other invisible forces are out there, secretly shaping the physical universe right under our noses? Keep observing, keep questioning, and I'll catch you in the next explainer.